We present our work on learning cooperative strategies for drone swarms using multi-agent reinforcement learning. The pursuit evasion problem has been a popular topic in controls literature over the past few decades, ranging from single evader versus single pursuer problems to multi-evader versus multi-pursuer problems. In this work, we will focus on the more challenging multi-agent pursuit evasion problem, where an evader drone team is assigned a mission to reach a goal with minimal velocity while avoiding being caught by a pursuer team. The pursuer team must defend the goal and catch evaders while having superior control capabilities compared to the evader team, while using one of two fixed policies: pure pursuit and augmented proportional navigation. In order to accomplish the more challenging tasks in multi-agent pursuit evasion, authors have proposed cooperative pursuit evasion strategies. Cooperative engagements may require increasing algorithm complexity and scale poorly with the number of agents. We propose multi-agent reinforcement learning as a tool for solving our multi-agent pursuit evasion problem. Specifically, we use multi-agent proximal policy optimization due to its effectiveness at solving multi-agent games. This requires learning only a single policy network that uses parameter sharing between all evader agents. The inputs to the actor are the local state of the current evader agent, states of all other agents in its team, states of all of the pursuer agents on the other team, and a one-hot vector representing which pursuer is targeting which evader. Additionally, we use a centralized value function that uses the global state of the environment. For further implementation details such as rewards, conditional events, hyperparameters, and training details, we refer the viewer to our paper. We train the evader teams for two different pursuer strategies: augmented proportional navigation and pure pursuit. In the augmented pronav strategy, the evaders have learned to take out the pursuers first by leading them into a collision-bound trajectory before going to the goal. This is mainly because the pronav strategy is more difficult to juke and avoid than the pure pursuit as shown on the right. Therefore, the evaders must lead them into a collision as quickly as possible, otherwise they will be caught by the pursuers. We use the more difficult to avoid pronav strategy for hardware implementation on Crazy Fly nanoquad rotors to demonstrate the sim-to-real capabilities of our approach. But before we deploy our ROS2 code, we test our implementation and train models on a software-in-the-loop simulator called Crazy Sim that emulates the Crazy Fly firmware on the desktop machine with gazebo physics and simulated sensors. This simulator also emulates the same communications pipeline with the actual control rate we would use on the real hardware. This allows us to tune our models and test our hardware code before deployment. In this demonstration, we will have the pursuers start near the spherical goal on the left and evaders on the right. Notice that the evaders first cooperate to lead the pursuers into a collision before going to the goal. Finally, we deploy our models and code to real Crazy Fly hardware and demonstrate that the strategy remains the same as in the simulation. Once a collision event or goal-reaching event occurs, we command the drones to hover near the occurred event with some offset in the position to avoid flying in the downwash of other drones.